Artificial intelligence is the broad, overarching objective of developing systems capable of simulating human intelligence to solve complex problems and make autonomous decisions. Within that broad boundary sits a specific operational engine, machine learning. Instead of relying on explicit, line-by-line programming to execute tasks, this subset takes a different structural approach. It focuses entirely on developing algorithms designed to learn strictly by finding patterns and relationships within massive datasets, allowing the system to make informed predictions on its own. If we look even closer, nested directly inside machine learning is deep learning. This highly specialized subfield utilizes artificial neural networks built with multiple interconnected layers. These deep neural networks have the unique mechanical ability to automatically extract hierarchical features directly from raw input. Using these terms interchangeably obscures how the architecture actually functions. AI is the destination. Machine learning is the vehicle that gets us there by learning from data, and deep learning is simply one highly specialized type of engine. Operating strictly within that machine learning boundary is another specialized field, generative AI. Standard discriminative models in machine learning are built to categorize existing data. Generative models operate differently. They learn the underlying distribution of a dataset specifically to create entirely new instances that closely resemble the original inputs. Alongside these is natural language processing, or NLP, a subfield that spans across both the broader AI and machine learning boundaries. NLP is concerned entirely with engineering the interaction between computer architecture and human language. It processes text and speech through structural tasks like tokenization and named entity recognition to achieve genuine semantic understanding. For a data scientist, identifying exactly which of these architectural subsets applies to their problem is the mandatory first step, long before a single piece of code is written or a model is trained. Once the architectural space is defined, the structural reality of the raw input data dictates how the machine will learn. Specifically, the entire process hinges on whether that data comes with predefined labels. In supervised learning, the algorithm learns from data that is already labeled with known outcomes. The goal is to minimize the mathematical difference between what the model predicts and what the actual documented results are. This supervised approach branches into two applications. First, classification, where the model sorts input into categorical bins. Second, regression, predicting a continuous trend. Conversely, without predefined labels, data spontaneously groups in unsupervised learning. Because there is no target outcome to guide it, the algorithm is forced to uncover hidden patterns and structures in the data entirely independently. This is the mechanism driving complex, open-ended tasks like anomaly detection and customer segmentation. An engineer does not arbitrarily decide which learning paradigm to use. The physical presence or absence of human-labeled data makes that operational choice for them. When obtaining a fully labeled dataset is too expensive or time-consuming, engineers use a hybrid approach called semi-supervised learning. This leverages a small amounts of labeled data to guide the learning process over a much larger pool of unlabeled information. There is also reinforcement learning. Here, an algorithmic agent makes sequential decisions, adjusting behavior through trial and error. It receives direct feedback as numerical rewards or penalties until it maximizes its cumulative reward. Understanding these paradigms lets us trace the machine learning model lifecycle, a rigid 10-step horizontal pipeline. The process moves chronologically, from problem definition through data collection, pre-processing, and feature engineering. It passes through model selection and arrives at model training. But the pipeline halts deliberately at step 7, model evaluation. An algorithm that has completed training is effectively a liability. It cannot be deployed into a production environment until its predictions survive the rigorous mathematical gauntlet of the evaluation phase. When evaluating a classification model, checking it for simple accuracy, the basic proportion of correct guesses, is an insufficient and dangerous way to assess operational risk. This confusion matrix compares predicted against actual labels. The green diagonal represents true positives and true negatives, perfect alignments. The real risk lies in errors. False positives are false alarms, and false negatives miss the positive instance entirely. Decoupling a model's overall error rate into exact failure modes is the only reliable way to diagnose underlying algorithmic weaknesses and prevent costly operational failures. From the confusion matrix, engineers extract specialized evaluation metrics. The first is precision, which measures the model's strict ability to avoid triggering those false alarms. We derive precision mathematically by taking the true positives and dividing them by the total number of instances the model predicted as positive, the true positives plus the false positives. If a bank builds a fraud detection model, precision is vital. A single false positive here means automatically freezing the account of a legitimate customer trying to buy groceries. Recall, also known as sensitivity, approaches the problem from the opposite direction. It measures the model's ability to successfully identify all actual positive instances hidden inside the dataset. To find recall, we take those same true positives, but this time we divide them by the total number of actual positive instances, the true positives plus the false negatives. Recall dictates the design of medical diagnostic tools. If an algorithm is scanning MRIs for tumors, a false negative means a severe, progressing disease goes undetected by the physician. Because optimizing a model to increase precision almost always degrades its recall, engineers must mathematically define exactly which type of error their specific business model can afford to tolerate. When a system cannot afford to heavily skew in either direction, engineers calculate the F1 score, which serves as the harmonic mean of both precision and recall. This provides a balanced, rigid performance metric, designed precisely for applications where both false alarms and missed detections carry unacceptably high operational costs. To summarize this performance holistically, the ROC curve and its area under the curve, or AUC, plot true positive rates against false positive rates at various threshold settings. This delivers a single scalar value that grades how well the classifier performs across every possible scenario. If an engineer is dealing with a multi-class problem rather than a simple binary choice, they scale this exact process up, calculating these metrics independently for every single class involved. Machine learning is an engineered process, bound by data constraints. Its real-world utility is governed by the initial data paradigm chosen in Step 1, and it is strictly validated by the unforgiving mathematical thresholds established during final evaluation.